Yeah. All right. I feel very privileged and honored to be invited to this conference. I have been to Japan several times, and I'm happy to have this opportunity to come on the 60th birthday of Toshiyuki Kobayashi. Today is his birthday, so as the first speaker this morning, I get the opportunity to wish him all the best and many more happy returns on this 60th. All right. I prefer to give a non-technical talk. I hope this will be accessible to most people in the audience. The context of my talk will be that G, a group, H, a closed subgroup, and there are two related questions that one considers. Related questions that one considers. So, question 1, classify irreducible unitary representations of G which appear. So I think the word is appear weakly in L2 of G mod H. And the question 2 is classify irreducible representations pi of G such that dimension of the Hom space Hom pi to C, which are H invariant, and these are supposed to be continuous linear forms, something which I will not emphasize because that would be unnecessary in the context that we will be dealing with. So these are two related questions, not quite the same, but closely related. I will be considering only question 2, for which so this lecture will deal with only question 2. Question 2. And here there is the more precise question. Here there is the more precise question. Question of understanding M pi, which is this dimension of the Hom space. So it may sometimes be 0, it may sometimes be infinite. We are mostly interested in understanding when it is non-zero and perhaps to understand the multiplicities also. So representations of G for which M pi is non-zero, so definition. Representations, irreducible representations of G for which M pi is non-zero are said to be H distinguished. Are said to be H distinguished. Sometimes when the subgroup H is understood, one drops the word H distinguished and one just says the representation pi is distinguished. There is a slightly is a slightly more general question in which one considers characters chi from H to C star, and one looks at Helm space H invariant phi to corresponding C chi, and when non-zero, such pi are called chi distinguished. Okay, so the classification of distinguished and chi distinguished representation has become a very important theme in the subject of automorphic forms and PRD groups, and it also makes good sense and is also an important question for real groups. In my lecture today, I will deal not directly with real groups, although most of what I say should have parallel for real groups. In fact, I will begin with one example in which I will talk about real groups. So, in this lecture, H will be the fixed points of an involution theta on G. So, in this case is the pair G comma H or G comma theta is called a symmetric space. So this is a case in which this dimension of the Helm space is known to be finite dimensional. So in this case, m pi equals dimension of this Helm space is known to be finite dimensional, and in some sense the question is to understand this function m pi as pi varies over all irreducible admissible representations. And the question of interest is to understand the function. So, one might say one looks at G hat. So, these are irreducible representations of G, and there is this mapping to n greater than equal to 0, which sends pi to m pi. And the question is to understand this function as precisely as one can. Okay, so there is a particular case which I have considered for many years, and a work which is still incomplete, in which one might say that this pair G comma H, where H is a symmetric subgroup of G, is a special case, But even in this special case, there is a very special case which is what I have tried to consider for this precise question. So, in an incomplete work, I consider this question. For what is called Galois symmetric space, Galois symmetric space. Which is for the pair for G comma H to be GE comma GF, where E over F is quadratic extension of local fields. So this is a symmetric pair. The Galois involution on E over F operates on GE, whose fixed points is GF. And the question there is to classify representations of GE which have fixed vectors for GF. And even this case is quite subtle. So I want to give one example of okay. So I want to give you one example of what we are talking about. So here we will look at GLNC and subgroup UPQ. And the question is to, so here the question is to understand these multiplicities M pi for pi any irreducible admissible representation of GLNC. And in this example, so let pi be a unitary principal series, pi is equal to coming from chi1 chi-n. So I should have said that in this case one knows, so this is a certain generality, that M pi is non-zero implies that pi is isomorphic to pi sigma. So where sigma is the Galois involution of GLNC with respect to GLNR, not with respect to UPQ. So since pi is isomorphic to pi sigma, if one translate, and this is a unitary principal series, and for simplicity I will assume that chi-i is not equal to chi-j. So since pi is isomorphic to pi sigma, some of those characters will be Galois invariant and some of the characters will get switched by the Galois xn. So suppose chi-i sigma equals chi-i for I from 1 to L, and then chi-L plus 1 sigma is chi-L plus 2, chi-L plus 3 sigma equals chi-L plus 4, and dot 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 chi-L L plus K minus 1 is equal to chi L plus K. So as I said that since the character...
excuse me, can I ask a question?
Yeah.
So what is sigma?
Sigma, as I said, is the complex conjugation. So it is not the involution which is coming from this, but it is Z goes to Z bar.
Okay.
Z goes to Z bar.
I see.
Chi bar.
Okay, thank you very much.
So I am rewriting the characters such that first few are left invariant under sigma and the rest are permuted. So these are distinct and they get permuted. So all together they are L plus 2k. So n here is L plus 2k, and in this example, one says that harm u of L plus u of k plus r, k plus s of pi comma c, the dimension of this is equal to binomial coefficient L choose r. So here where r plus s is equal to L and r is equal to 0. So in particular, sum of these multiplicities Harm spaces over u k plus r, L plus s, r plus s is equal to L. This is equal to sum of the binomial coefficients. So I have chosen this example to say that the explicit multiplicities and for which group and for which representations they are non-zero is quite subtle, and even this calculation I think is somewhat non-trivial. One way to think about this example is that in the flag variety of GL and C, the number of open orbits is this. Okay, so indeed a very precise answer can be given to this general question to understand what is m pi over all pi, and that is what I have attempted to do in a manuscript which is still incomplete. But in today's lecture, I want to discuss less precise question for which answers can be provided in more generality. Less precise, but more general questions can be answered. So instead of this question, which is very specific, Galois symmetric space and all multiplicities one wants to understand, and that involves, this work is related to somehow the theory of base change and fibers of the base change mapping for L parameters. Whereas what I am going to talk about today is more straightforward dealing with representation theory. So as I said, instead of precise answers, precise questions and precise answers, we will ask more cruder questions for which precise answers can be given. So I begin with, so here we will deal with general symmetric pairs, with general symmetric spaces. Okay, so I begin with some names. So there was this work of Ash, Ginsberg, Galois, Allen, 1993. Yeah, so I already said that the lecture from now on will not deal directly with real groups, although real groups are very much part of what we do. We will not deal with real groups. On the other hand, what I talk about is valid equally well for both periodic fields and finite fields. So we will consider groups over periodic as well as finite fields. So in the main part of the lecture, we will look at both finite fields and periodic fields. This notion, okay, so a pair, so they make a definition, a pair G comma H is a non-vanishing pair if there exists a cuspidal representation phi of G which is distinguished by H. So they study this mostly in the context of a automorphic representation, but this question makes very good sense both for automorphic form as well as for groups over periodic fields and for finite fields. One can talk about those pairs for which there is a distinguished cuspidal representation, and they have many examples of pairs which are vanishing pairs. So maybe I can just to begin. Let me give you an example. So in the case of GLN, if you look at GLM plus N, which contains GLM cross GLN, then this is a vanishing pair, if absolute value of m minus n is greater than 1. So A, B, GL2M contained in SP2M is also a vanishing pair. Whereas the other symmetric space GLM contained in SOM is not a vanishing pair. So in fact, this work of theirs does not have a real theorem which says that there is a cusp form or cuspidal representation which is distinguished if and only if something happens. I think they are interested in certain set of examples, and they analyze several examples. So it is based on examples. So this is the work of Ash, Ginsberg, Rales, and then I want to mention this recent work of Benoit and Toshiyuki Kobayashi. So they classify pairs G comma H such that L2 of G mod H is tempered. And one may call these pairs tempered pairs. May call these tempered pairs. And unlike that work, which as I said is a bunch of examples, this paper is rather complete. It has both a theorem, and as consequence they work out many examples. So let me give you the same examples there. GL M plus M containing GLM cross GLN mod M minus M is less than equal to 1. So for this to be a tempered pair, GL2M containing SP2M is not a tempered pair, and C GLM containing SOM is a tempered pair. Okay, so this brings me, so there is that work for cuspidal representation, there is this work for tempered pairs, and this brings to my own work. So in a paper, Advanced Edge 2019, I discuss pairs, symmetric pairs, G comma H such that there exists an H distinguished generic representation. So what I wish to do in this lecture is to briefly talk to you about this. So I should begin by just, I guess this is a rather common notion, but still, so recall that generic representations are defined only for G a quasi-split group. So maybe first time I should say that in full. Quasi-split group. And containing, so therefore containing a Borel subgroup B, containing B and a torus and a U. And one fixes a character psi from U to C star, non-trivial on all simple spaces, simple roots. And then one says that pi is generic if and only if this Hom space Hom U of pi with C psi is non-G. So these generic representations are they are generic in two sense, at least for GLN. Most representations are generic, and they are also generic in the sense that their dimension tends to be the largest possible dimension. So in many ways, generic representations are the most important for the theory of automorphic forms. This work discusses generic representation, discusses distinction of a generic representation. So I will state the precise theorem, but somehow the upshot is that example exactly same list as in the case of as Galois and okay. So this is what I want to discuss here. Okay. So for generic representations, G must be quasi-split, quasi-split group, which we assume in the rest. Assume now on, and H is G theta, where theta is an involution of G. So in this case, definition, the symmetric space G comma theta or G comma H, where H is the fixed point or connected component and so on. The symmetric space G comma theta is said to be quasi-split. If there exists a Borel subgroup B contained in G such that B intersects with B theta is a torus. So the group is quasi-split, and then one talks about the symmetric space being quasi-split. Okay, so so this I did not learn, but I think okay, maybe it is here. Yeah, all right, good. So so here is the theorem. So let F be either a finite field or a non-Archimedean local field. G a quasi-split reductive group, H is equal to G theta naught, or in fact it could be also its derived subgroup. In fact, so maybe I put that already here. So it's a stronger theorem. Then there exists a generic representation of G distinguished by H if and only if G comma theta is a quasi-split symmetric space. So there is a very neat answer and something which can be expressed in a very compact way, that there exists a generic representation if and only if something is true about the symmetric space. So I will make a few comments about the proof of this theorem, but before I do that, in fact, it is, I think, there is another nicer way to state this theorem. So, another way to reformulate this theorem by making a condition on some symmetric space over real numbers. Another way to reformulate this theorem, in which we refer to symmetric spaces over real numbers. So even though these theorems are theorems about finite fields or periodic numbers, we want to make a reinterpretation of this theorem which refers to symmetric spaces over R. So for this, recall that if E is any algebraically closed field, G a reductive group over E, it makes sense to talk about G over C. Makes sense to consider G over C. Because any reductive group is, for example, GLN or SLN or SP or SOPQ, and whether it is defined over algebraic closure of a finite field or algebraic closure of a periodic field or over complex numbers, it's the same root datum which allows one to define a group. So I want to refine this notion, something which I have not seen discussed too much. So similarly, the pair G comma theta has a universal character, has a universal nature. So which means that even if the group and the involution was given over a given field, you go to the algebraic closure of that field, and then you can transfer this data to G comma C, i.e. That is from any pair G comma theta over F over E, pair G comma theta over E, there is a canonical way to associate a group G comma theta over C. And such that the connected component of the fixed point of theta, which is a certain reductive group, and the connected component of the fixed point of theta in G here, those groups correspond by this process, such that G theta naught corresponds to G theta naught, and under this correspondence, okay, so that will come later. No, so there is one part to this correspondence. Under this correspondence, quasi-split symmetric spaces go to quasi-split symmetric spaces. Spaces go to okay. So next I want to recall for you this classic theorem of Cartan, which may have come up in these lectures, Cartan's classification. Which says that reductive groups over R, reductive groups over R are in bijective correspondence with G over C together with theta. So if you are given a complex group together with an involution, it defines you a uniquely a reductive group over R, which has the further property that so this group GR has the property that given that data, the GR is a subgroup of GC such that GR intersected with G theta C is the maximal compact. of GR. I should maybe more simply say that GR is a subgroup, is a real form of G, and theta preserves GR and is the Cartan involution of GR. So there is a bijective correspondence with groups over R and GC over theta. And then the observation here is that a symmetric space G comma theta over C is quasi split if and only if GR. So this is the group maybe associated to theta, G theta R. So the symmetric space is quasi split if and only if the corresponding real reductive group is quasi split over R. So as a upshot of all this, whenever you are given a symmetric space over any field, you can transfer to a symmetric space over complex number and get a real group. And it is eventually whether that real group is quasi split or not is the condition for this theorem. And now I will quickly run through these examples. So example, in the case of GL M plus N containing GLM cross GLN. So you see we are doing this over general field, finite field, periodic field, real field, etc. But for this symmetric space, the corresponding real group, the corresponding G theta R is nothing but UMN, because you want its maximal compact to be the fixed points of that involution. So its maximal compact is UM cross UN, and which is a form of this GLM cross GLM. So this and this is, of course, now we are in the classical situation of knowing that this group UMN is quasi split if and only if mod M minus which is quasi split. Quasi split if and only if. And so B. In this example of GL2M containing SP2M, we would be in the real group GLM of the Hamiltonian, and this is not quasi split. Not quasi split. And in the case of GLN and SON, we would be in the case of just GLNR, and which of course is split. So perhaps since one knows the real groups very well and one can quickly come up to which real groups are split, quasi split or not of that kind, it allows you to quickly conclude which symmetric spaces are quasi split or not. Okay, so yeah, I still have 10 minutes. So I want to, okay. So maybe before I go on,
I said that the examples which come up in this Ash, Ginsburg, Rales, Benoit, Kobayashi, and in this generic case, they all seem the same. So in that paper of mine in Advances in 2009, independent of this perspective, but from just based on examples, I had proposed the following. So conjecture. So in this case, G is quasi-split over F. Yeah, so let us say F either periodic or F equals R, theta and involution on G, H is equal to G theta naught commutator. Then now I take H to be G theta naught which we are shown. Is also quasi-split. Let pi be a tempered representation of G distinguished by H. H. Then, there is the notion of what is called an L packet associated to a representation of a reductive group over local field. There is the notion of L packet. So then there exists a generic member, a generic representation in the L packet of pi, which is distinguished by H. So what that means is that if there is a tempered representation which is distinguished, then there is also a generic member which is distinguished. And for generic member, one has that simple-minded answer. And therefore, for tempered representation also, that simple-minded answer should exist. And as far as I could check in the examples of Benoit and Kobayashi, all the examples that I could check, and I guess it looks reasonable, that at least if there is a no generic representation which is distinguished, then their theorem also says that they are no tempered representation. But this is a more precise one. It says more precisely that if there is a tempered representation distinguished by H, then in the L packet, the generic member is also distinguished by H. So this conjecture, this conjecture was made in analogy with a conjecture of Shahidi, conjecture of Shahidi, which is for this conjecture for G cross G. So, if you think about this symmetric space, then there is a famous conjecture of Shahidi that every tempered L packet of a group contains a generic member. And so somehow this conjecture was based on example, and there has been some recent works of Dmitry Gurevich and Atan Sayag, which somehow are a step in a direction to prove this conjecture. Okay, so now I finally want to make a few comments about the proof of this theorem, which tries to understand generic representations of G distinguished by H. So, to understand genericity means something on U. So, basically what it means is that, right, so I was hoping not to have to rub anything. So, maybe I will do it here. One cannot go halfway, so I think, okay. So I want to give some comments on the proof. Comments on proof. So existence of a generic existence of H distinguished generic representation of G is equivalent to understanding this double coset H mod G mod U. Rather, what we want to understand is the action of U on this space G mod H. And then we look at the orbits of U on G mod H, and suppose the orbits are U upon Ux for the point X. So suppose that the orbit, orbits are of the form, orbits of U are of the form U upon some Ux. You see, on G mod H the group U operates, and therefore orbits are U upon some stabilizer. So instead of proving that a particular representation on G mod H has a Whittaker model, we just want to know whether this whole space has a Whittaker model. And so this U mod Ux has a Whittaker model. If and only if, so you have a unipotent group and a unipotent subgroup of a unipotent group, and one knows that this has a Whittaker model if and only if there are no simple roots which are contained there. There does not exist any simple root space U alpha inside Ux. There are no simple roots, and then you will choose an appropriate linear form on U, trivial on Ux, and it will be non-trivial on U alpha. So from this data, you eventually the theorem says that if there is an orbit which has this property, then there is another orbit on which U operates without a fixed point. You know, to say that the symmetric space is quasi-split is equivalent to saying that there is an orbit on which U has no fixed points. So, you know, the involution theta is there, and it's a question of roots and weights that I need to deal with. I mean, in the beginning it looks a bit surprising that just because there are orbits U by Ux where Ux doesn't contain root spaces. So, you know, these orbits may be as small as 1 dimensional, which contains no root space, but from such a small orbit, eventually you can construct an orbit which is dimension U, no stabilizer. So it looks quite impressive. It is the same impressiveness somehow as saying that a generic representation to begin with has just one character on U. But then a generic representation, the dimension of a generic representation is very large. So somehow from one character of some non-degenerate kind, you construct a very large dimensional representation. So perhaps it is similar analysis. So there is some manipulation with roots and weights, but these are all in the domain of algebraic groups, and I do all this analysis mostly over algebraically closed field. So that analysis can be done over finite fields, over any field. All right, so I think I am done with my time, and I will end here. Thank you very much for your attention.